We're continuing section 15.3, geometry of partial derivatives. And so the discussion we had so far is that the planes x equal to a and y equal to b intersect the surface z equal to f of x and y. That's the graph of the function z equal to f of x and y, and curves z equal to f of a and y and z equal to f of x and b respectively. The partial derivatives are the slope of the tangent lines to the two curves. Now, the tangent line to the graph of z equal to f of x and b contain the point a and b and f of a and b and has direction vector 1, 0, f sub x of a and b. So how does this work? What we know is that because we were basically finding the tangent line to z equal to f of x and b, we're looking at the plane y equal to constant b, and therefore there is no change in the vector that in the tangent line in the direction of y. And we also know that on the plane x z, the slope of the line is f sub x of a and b. So one step in the x direction, z direction, you have f sub x of a and b. In the similar manner, the tangent line to the graph of z equal to f of a and y, this time we're setting x equal to a constant, contains the point a, b, f of a and b, and has direction vector 0, 1, f sub y of a and b. This time x doesn't change, and every step in y changes z by f sub y of a and b. So that's another way of thinking about it, because the discussion that we had, the slope of the tangent line, were either in y equal to b or x equal to a, but we want to have the tangent line in 3 dimension. So write the equation of the tangent line in 3 dimension, so we need a vector of direction, and these two give you the vectors of direction. Example 2, find the partial derivatives of f of x and y equal to x times y plus 1 minus x squared. Then calculate the tangent line to the graph of f at negative 2, 2, and negative 10 in both the x and y direction. So how do we go about doing this? First, let's find the derivative with respect to x. So derivative partial with respect to x is going to be, when we're finding the partial with respect to x, remember we're considering y to be constant. Oh, that means y plus 1 is a constant. Let's say y is equal to number 2, and so 2 plus 1 is equal to 3. Therefore y is going to be y plus 1 is going to be a constant. So taking derivative of that, we'll review with y plus 1. So taking derivative of this entire thing leaves you with y plus 1. Then derivative of negative x squared is negative 2x. How about derivative with respect to y? So derivative with respect to y is equal to, this time x is the constant multiplying y plus 1, but notice it's a constant, so you take the derivative of y plus 1 and that would be just 1, and it would be 1 times x, which is x, and then derivative x squared is just a constant to the power 2, which is going to be a constant. Let's say 2 to the power 2 is going to be a constant, so you end up with x. And so when you want to find the tangent line of f at a certain point, first of all, plug in that point in the in your partial derivatives. So I'm going to do partial derivative with respect to x at -2 and 2. That's the x and y I'm plugging in. And what do I get? 2 for y and -2 for x. It gives 2 plus 1 plus 4. That's 7. Now, same thing for derivative with respect to y, evaluated at x and y. And that would be just -2. What would the direction vector be for tangent line on in direction x? And so that would be 1, 0, and 7. What would that direction vector be for in direction y? That would be 0, 1, and -2. And then we want to find the tangent line to the graph of f, and that is basically for this one, for this vector, you will have -2, 2, and -10 plus t times 1, 0, and 7, and this would be r1t, r sub x t, and then r sub yt is going to be r sub yt, again the point and t times the direction plus t times 0, t times 0, 1, -2. And again, when you're, for example, when you're finding Rx of t, then you can also multiply t through and write it as a vector instead of a sum of a vector and a multiple of the other vector. And also for R sub y of t, same thing is true. One thing to notice between the two of them, one thing to notice is that here x and y were given and a z value was given, but we don't really need to have that z value given to us. All we need to do is to plug in -2 here for x and 2 for y and find that z value. And so a different question may ask you to do that versus this question actually calculated the z. If you plug in -2 for x and 2 for y, you will end up with -2 times 3, which is -6, and then -4, which makes it -10. That's the z value. So just just notice if you need to calculate z or not to find the equation of the tangent line.